There are moments in the history of science when the universe seems to lean closer, almost as if it wants to see whether we are paying attention. It usually happens in the quiet hours, in the silence of a control room, or the soft hum of a server farm processing data. A small fluctuation in a graph, a faint distortion in a spectrographic line, or a signal so soft it might be mistaken for noise until it starts to repeat. In those moments, something inside us shifts. The familiar becomes uneasy. The expected becomes fragile. We find ourselves whispering a question humanity has asked for thousands of years, staring up at the same dark canopy. What are we truly looking at tonight? That question begins nearly 4 billion kilometers from Earth, in a region of space quiet enough that the background whisper of the solar wind is usually the loudest thing you hear, if you could hear anything at all. It begins with an interstellar traveler named 3I ATIAS, the third confirmed object from another star system to ever pass through our solar neighborhood, and it begins with a reading, tiny and improbable, detected in late 2025, a shockwave forming behind the object, not in front of it. To understand why this is so strange, so fundamentally unsettling to the people whose job it is to model the physics of our solar system, we need to go back to the moment it first appeared on NASA's dashboards. The alert wasn't dramatic. There were no sirens, no blinking red lights, no frantic phone calls to the White House. It was simply a deviation in a model. A thin ripple in magnetometer data recorded by solar orbiting spacecraft that usually ignore objects as small as 3I ATIAS. But the pattern caught the attention of a researcher at NASA's Goddard Space Flight Center, who was reviewing routine telemetry. When they first saw the internal note, just a single line that read, anomalous wave structure, source uncertain, the immediate assumption was a calibration error. That is the safe assumption. Interstellar objects are supposed to be quiet. They are supposed to be inert rocks tumbling through the void. They don't produce meaningful waves. And if they do, the wave should form in front of the object as it plows through solar plasma, creating a bow shock, similar to water piling up in front of a moving ship. But as the data accumulated over the next hours, then days, the impossible began to settle into the realm of the measurable. The wave was behind it. What exactly are we looking at here? To explain that, we need to picture the environment 3I ATIAS is moving through. Space isn't empty. It is filled with charged particles from the sun, the solar wind drifting outward in a constant flow. When a solid body moves through this plasma, it forms a disturbance. Comets, asteroids, spacecraft, they all do it. It is basic fluid dynamics applied to astrophysics. But 3I ATIAS, based on multiple instruments, seemed to be producing the opposite. A wave coherent, structured, and persistent was forming downstream, following the object like a faint echo pulled behind it. Imagine a speedboat traveling across a lake and leaving a wake ahead of itself rather than behind. Imagine a meteor streaking through the sky while dragging turbulence forward, not backward. These things don't happen. They don't fit our models of motion through any fluid, whether air, water, or plasma. And yet, that is exactly what the reading suggested. When the anomaly first circulated among NASA teams, the initial response was caution. The possibility of sensor interference was high. Cosmic rays can mimic patterns. So can fluctuations in the spacecraft's magnetic hardware. But the readings weren't coming from one instrument. They were coming from several. Multiple spacecraft, different positions, different baselines. ACE, DECODE, VR, STERO, even the Parker solar probe caught the faint signature as it skimmed through the inner heliosphere. These platforms rarely agree perfectly on small anomalies. But here they were, sketching the same shape, the same direction, the same improbable shockwave. This was when the conversation changed. What began as an oddity became a puzzle. A short anomaly turned into a potential discovery. Some of the researchers tried to model it as a density cavity. If 3I ATLAS were outgassing at a rate far above normal, the gas could create turbulence that extended downstream. But the coma wasn't large enough for that, and the tail behavior didn't match. Others propose electromagnetic coupling. Maybe the object had a charge distribution interacting with the solar wind, but that would have produced a different signature entirely. One model suggested the shockwave might be the product of a delayed magnetic reconnection event, something like a ripple propagating backward. But again, the data didn't match. The propagation was too coherent, too clean. It was almost as if the wavefront were being maintained. Sitting at a desk past midnight, staring at the composite graph, one might notice the line didn't jump or crackle the way noise does. It flowed smoothly, steadily, almost rhythmically. And it forces the question that a lot of researchers ask in private: what if 3I ATLAS is interacting with the solar environment in a way we haven't modeled yet? Not something supernatural, not something dramatic, but something new. In astrophysics, new is a dangerous word. It requires evidence, humility, and a willingness to let go of assumptions we didn't realize we were holding. But it is also the word that drives discovery. To see how strange this really is, let's take a moment to remember Oumuamua. You might recall that when it passed through the inner solar system in 2017, something about it didn't behave the way we expected. Its acceleration deviated slightly from a purely gravitational path. Not enough to suggest anything extraordinary to the casual observer, but enough to raise questions among the experts. The debate lasted years, and in some ways it still continues. But what made Oumuamua's case famous was not the anomaly itself, it was our struggle to fit the anomaly inside our existing frameworks. 3I ATLAS is doing something similar but in a different arena. Instead of motion, it is the object's plasma interaction that is challenging our understanding. And unlike Oumuamua, 3I ATLAS is emitting a signature that multiple instruments can verify in real time. This is the scientific equivalent of lightning striking twice, but in two different weather systems. So we return to the question: what creates a shockwave behind an interstellar object? Let's walk through the options. The first possibility, and probably the most conservative, is that 3I ATLAS is moving through a region of solar wind turbulence that creates a delayed wave structure. The solar wind isn't uniform. It is lumpy, chaotic, textured like smoke drifting from a fire. If the object passed through a region of unusually dense plasma, it could theoretically leave a temporary trailing disturbance that looks like a shockwave. But the wave NASA detected isn't fading. It is stable. Hours became days. The structure is still there, following the object like a shadow sculpted into the magnetic field. Another possibility is that the object is rotating in such a way that it is shedding particles in a directional pattern. Comets do outgas, and that can create jets, but jets don't create systemic shockwaves. They produce weak, chaotic turbulence, not the clean, forward-propagating ripple we see here. And 3I ATLAS is not behaving like a typical comet anyway. Its activity curve is uneven, its brightness fluctuates in strange intervals, and its color signature shifts between observations in a way that is unusual. Some propose that the shockwave could be a relic field the object carried from interstellar space. Imagine a body drifting through charged plasma for millions of years, accumulating a sheath of magnetic structure. As it enters our solar wind, that structure could unravel, creating turbulence behind it. But calculations show that any such field would dissipate quickly. Interstellar magnetic drift does not maintain coherence long enough to produce a wave pattern this stable. And then there is the idea, still speculative but worth mentioning, that the shockwave might not be a reaction to the solar wind at all. It could be something internal, not artificial, just physical. Something about the object's composition interacts with the environment in a way we haven't seen before. Maybe superconductive minerals. Maybe exotic ices. Maybe a shell of material that responds to electromagnetic forces differently than expected. Interstellar chemistry can be strange. Objects born around other stars can carry compounds we have never observed up close. If this is the case, 3i Atlas might be teaching us something new about the diversity of matter in our galaxy. Something subtle, something that doesn't rewrite physics but expands it. Sometimes that is all it takes, a small correction that reveals a much larger truth. As NASA teams continue to track the wave, one detail grew even stranger. The shockwave seemed to oscillate slightly, periodically, as if the wave had a heartbeat. Not biological, of course, but cyclical, a repeating rise and fall in amplitude like the ticking of a clock. Every few hours, the pattern reset, a ripple, a collapse, a ripple again. This was when researchers began comparing the timing to the object's rotation period, and to their surprise, the oscillation matched. Not perfectly, but close enough to be meaningful. Whatever was creating the shockwave was tied directly to how 3i Atlas turns in space. Reading that analysis in a quiet room, lit only by the pale glow of a monitor, one realizes the implication: rotation, modulated plasma interaction. That is not impossible, but it is unexpected. And if it is happening, it tells us something profound. It tells us 3i Atlas isn't just passing through the solar system, it is interacting with it actively, dynamically, in a way that no interstellar object we have ever observed has done before. You might ask, does this mean the object is artificial? No, there is no evidence for that. But does it mean the object might be more complex than a simple chunk of rock or ice? That is possible. Interstellar objects can be layered, fractured, porous, crystalline, or metallic. They can be shaped by radiation from distant stars. They can carry the fingerprints of environments completely unlike our own. The wave could be telling us about the object's internal structure, not its intentions. Still, the mystery remains: why behind, not ahead? The answer may come from how magnetic fields behave around rotating bodies. If the object has a patchy composition, regions that conduct differently, regions that hold charge differently, the interaction with the solar wind could reorganize those fields into a trailing pattern. Something like a wake, but inverted, not hydrodynamic but electrodynamic. As one researcher put it in a private memo, this isn't a fluid wake, it is a topological one, a magnetic shadow shaped not by motion alone but by structure. And if that is true, then 3i Atlas might be the first interstellar object that lets us study a foreign magnetic topology up close. A cosmic fingerprint from another star system carried for millions of years and now brushing against our sun's breath like a whisper from far away. Still, one keeps coming back to a moment early in the analysis, when a colleague looked at the evolving graphs and said almost quietly, "I don't think we're wrong. I think we've never seen this before." And there was no excitement in his voice, just a kind of reverent curiosity, the kind scientists feel when they realize they are standing at the edge of something they don't yet understand. The shockwave continues today, faint but unmistakable. As 3i Atlas moves past perihelion and begins its long outward journey, the wave may weaken, it may intensify, it may change form entirely. But whatever it does next, it will help answer a question we rarely get to ask with such clarity. What happens when matter from one star system drifts into the electromagnetic breath of another? We tend to think of the universe as static, quiet, predictable. But it is none of those things. It is a sea of interactions, collisions, distortions, and brief encounters between worlds that will never meet again. Every interstellar object is a message in a bottle, not written for us but readable if we are patient enough. And so we watch, we measure, we question, because that is how discovery works, not through certainty but through attention. What we know now is simple. A shockwave behind 3i Atlas should not exist, but it does. And the fact that it does invites us to imagine what else might be out there. What other signatures, anomalies, or quiet surprises wait in the dark between the stars. Maybe years from now, we will look back on this reading the way astronomers look back on the first detection of cosmic microwave background radiation, a clue that seemed small at the time but opened a new chapter in our understanding of the universe. For now, 3i Aetylos drifts onward, carrying its mystery with it, and we, standing on our small blue world, keep listening because the universe is whispering again. And this time, we are paying attention. The silence that surrounds us is not empty. It is pregnant with information, waiting for the right instruments and the right minds to decode it. The implications of this extend far beyond this single object. If 3i Aetylos is interacting with the solar wind in this unique way, it forces us to reconsider the environments of other solar systems. If we assume that 3i Aetylos is a representative sample of the debris floating in the interstellar medium, then the galaxy is filled with objects that possess these complex interactive properties. It suggests that the formation of planetary systems involves processes that create highly structured, perhaps even conductive, or magnetic materials that eventually get ejected into the void. This changes the way we look at the formation of our own solar system. Did we eject similar objects billions of years ago? Is there a piece of Earth or Mars ripped away during the late heavy bombardment, currently creating a shockwave in the solar wind of a star on the other side of the Milky Way? The connectedness of the galaxy becomes more tangible when we see these interactions. We are not isolated. We are downstream from someone else's history, and someone else is downstream from ours. Furthermore, this discovery challenges the way we build our detection grids. Our current systems are designed to look for mass, for heat, for light reflection. They are designed to spot rocks. They are not necessarily tuned to spot subtle magnetic wakes or trailing shockwaves. If this is a common feature of interstellar objects, we might have been missing them for decades simply because we were looking for the wrong signature. We have been looking for the boat, not the wake. This realization could lead to a new generation of sensors, new algorithms designed to scan the solar wind for these topological shadows. It opens up a new branch of observational astronomy, interstellar plasma dynamics. It is a reminder that in science, you often don't find what you are looking for. You find what you are capable of seeing. And as our capability to see improves, the universe gets stranger and more beautiful. The oscillating nature of the wave, tied to the rotation, adds another layer of complexity. It suggests a non-uniform surface. Perhaps one side of 3i Aetylos is covered in a material that is highly conductive, while the other is insulating. As it spins, it acts like a switch, turning the interaction on and off, pulsing the solar wind. This kind of material differentiation is rare in small solar system bodies, which tend to be fairly homogeneous, rubble piles or dirty snowballs. A differentiated surface implies a complex history. Perhaps it was part of a larger body that differentiated chemically before being shattered. Or perhaps it was subjected to intense radiation on one side for eons as it traveled between stars. The story of its journey is etched into its surface, and now that story is being read by the solar wind and transmitted to our sensors as a rhythmic pulse. It is a heartbeat from the deep past beating in the present. As the data continues to pour in, the scientific community is mobilized. Papers are being written, models are being run, and arguments are breaking out in university hallways. This is the healthy noise of progress. The impossible, shockwave, is no longer impossible, it is data, and data demands an explanation. Whether that explanation turns out to be a new class of material, a new understanding of plasma physics, or something even more exotic, the result is the same. We know more today than we did yesterday. The universe has revealed a card it was holding close to its chest. It is up to us to figure out what the rest of the hand looks like. The tracking continues. The object moves further away every second, but the data it left behind will be analyzed for years. It is a ghost in the machine, a ripple in the calm, a whisper in the storm. And as long as we keep our eyes open, the universe will keep giving us reasons to wonder. The silence is not a lack of signal, it is just a signal we haven't learned to hear yet. But with 3i8LAS, we are learning, we are listening, and the cosmos is speaking back.